Welcome to another incredible edition of Comet Algebra. This video is for Algebra 1, Chapter 6, Section 6, Trend Lines and Correlation. Scatter plots, we use them to see the relationship between two sets of data. And we look at them to see if the points sort of are lining up in a linear direction. And then a trend line can be drawn in to show this relationship more clearly. Let me just draw an example of a scatter plot here. Let's say this scatter plot is of your income the first 10 years you have a job. I don't know, whatever your starting pay is right here. And let's say after 2 years you got a pretty good raise because they valued your service. And then the raises were a little smaller over the next few years. But once you hit year 5, you got a pretty nice raise, and then they were, and so on like this. So sort of linear. Well, definitely linear, but not absolutely perfect. If we drew in the line, it would not touch every single point, but clearly this relationship is linear. Now, human beings can draw in an estimated regression line or line of best fit, but graphing calculators do this way more accurately than a human being ever could, because the calculator averages out the distance between each point and draws it in, like I said, much better, much less error than a human being. So very often we're going to use our graphing calculators to find these equations for us. But the calculator will never be good as your mind in judging what type of relationship you see on the scatter plot. Sometimes these dots will line up in sort of a parabola shape. Then we're looking for a quadratic regression line. If they line up linear, we're looking for a linear regression line. So that's up to the human being to see that and judge that. So now a couple terms to know in working with scatter plots. When you are doing interpolation, it means that you're making predictions that lie inside your data points. So we know the exact income that we got on these year long, and it would be possible that you might have gotten some monthly increases in between, 0 and year 1. So if you're asked to do interpolation, you might be asked to use the graph and find what the income would have been at, let's say, 2.5 years. The 2.5 year point would be right here, right where that blue X is. And that blue X is inside all of these red X's. It's within the data points. And that can be clearly seen on the graph. We could find the equation and calculate it at 2.5 years. Now, outside the data points, when we're talking about extrapolation, that means using our line and predicting where would we be at the 20-year point. Well, we could follow this graph, this line on, and continue this out to 20 years and then see where it leads us. But that prediction outside the data points is a little more risky because there's factors that could happen. You could get a promotion and earn way more money, or the company could close down and you could be starting over at a different job. There's just a lot of variable factors that goes into things when you're extrapolating. So the question then is, which do you think is more accurate? And if you said that when you're doing interpolation, if you said that was more accurate, you would be right. That it's just a lot safer to make predictions inside here, inside these data points, because it's already proven what happened before and after it. Once you get outside the data points, however, a lot more unknown factors can come into play. So please know those two words. The next term we're going to discuss is linear correlation. And this would describe how closely or how tightly the data points are clustered along the trend line. This particular example I drew here of the income, these points are clustered pretty tightly to this regression line. We don't have some wild ones out here and down here. So this is a pretty strong correlation. And there's a number, a value of this we'll look at. This number describes how closely the data points are clustered along the trend line. When most of the points are close to the line, there is a strong correlation. Trend lines with strong correlations make better predictions, and you can be more certain of them. And mathematicians in business, they're asked to make predictions about sales or costs. And if you're going to do that, you want to have a really nice, tight, linear correlation to your line so that you can be confident in telling the boss, yes, I can make good predictions. Otherwise, if your correlation is very low, you might even tell the boss, I can't predict. Things are just a little too spread out, a little too much variance in the data. These 5 pictures are examples of different correlations. Now, just like when the slope of the line was going uphill from left to right, that was a positive slope. Well, likewise with correlation. This first picture shows a strong positive, where the data points are pretty tightly clustered, definitely linear, and definitely going up in the positive direction. So that's a strong positive. When your data points are all over the place like this, you can't really say anything about correlation. There's very little or even almost no correlation. And again, going downhill from left to right, that was a negative slope. Well, this would be a strong negative correlation where they're tightly grouped together. In this fourth graph, the points are sort of trending in an upward direction, but they're very spread out, very much away from the line that we would attempt to draw in the middle here. Therefore, this shows a weak positive, and likewise, they're trending down sort of, but not very tightly clustered. That shows a weak negative correlation. A perfect correlation, if we plotted a graph with data points and they happen to line up perfectly. If they line up perfectly, a perfect correlation is when the R squared is 1. 1 is perfect. Most of the time it's less than that. And we'll be talking about how to have the calculator display this correlation later. It's a very involved, very complicated calculation, so we are going to use our calculators for that. The next thing I'd like to do in this video is go through the steps of creating the scatter plot and finding the regression line on your calculators, and I thought we would turn to your assignment and do something some work from there. So could you turn to page 266 in your book, and let's go through the steps for problems 6 through 10 together, and then that should really help you with the rest of the assignment. So for number 6, we're asked to make a scatter plot of the data and describe the linear correlation of that data. So could you, for the first step, enter those 2 sets of data, the X and the Y, on the list. Could you please press the Stat button and select the Edit, and then the lists will pop up. So enter the X's on list 1 and the Y's on list 2. After you have your data on the lists, now step 2 is to turn on the stat plot. So could you please hit it's the second function of the Y equals key, and then select stat plot 1, and when it's blinking, the cursor is blinking on the word on, could you hit enter, and then you've turned it on. Step 3 now is to adjust the window settings. So hit the window key, and we look at our data from the table. The highest X value we have is 13. So we want to set the X max a little higher than our highest value. So why don't we just pick an X max of, let's say, 15. And our y max needs to be bigger because the highest y value that I see on our table is 57.5. So don't use that as your y max. I really shouldn't have written that there. Let's just go up to, let's just say 70 for the y max. And now hit graph and let's take a look at it. And if you entered everything on your calc and you turned on the scatter plot or stat plots, this is your calc screen, should look something like this. You should see all 5 points graphed. And now we look at it and we use our human reasoning to ask, is this linear trend or is it a quadratic trend or maybe something else that we'll learn later? And this is clearly linear. So now we know that yes, they look linear. We're going to find the linear regression line. So going back to your calculator, and so this is something that you would draw, like this would be your step 6. I put the whole calc screen. When you draw a scatter plot, typically we just draw a first quadrant graph. You would just do that much of it on your paper. And then you would describe it. It is definitely linear, and also for number 6, we would say that this has a very strong positive correlation because, I mean, they look like they're almost lined up perfectly. I can't really tell, so we put our line on there. But then that's number 6. So now number 7 says, determine the equation of the trend line. So since we have determined it's obviously a linear regression line, that is called a lin reg on the calc. So please go back and to your calculators and just press the stat button, and this time arrow over to the calc menu and a whole menu comes up. Scroll down it and select lin reg. And after you select that, you have to hit enter about five, maybe 6 times. I didn't really count. And then on your screen it should say at the top of it y equals ax plus b, and then it tells you what a and b are, so you plug those in. So for your number 7, you would write y equals 2.5x plus 25, and that's our regression line. It's really kind of cool. You don't have to do this, but it's cool to go to your y equals key and type this in. And after you type it in, you can hit graph, and then you can see it'll put this equation right over the top of your scatter plot, and it'll draw this line in, and then we can see that the line does go perfectly through all those points. And it just kind of confirms what we knew. This was a very strong positive. And it's kind of neat to see in your calculator. So now for number 8, it says use your equation to predict the value of y when x is equal to 3.5. So now all you need to do, you have the equation, you take this 3.5, put it in for x, multiply it, and do the math. You'll come up with an answer for number 8. Number 9 is practically the same thing. They want us to find the value of y when x is 20. So take this 20, put it in here for x, and find that y that goes with it. And then number 10 says, does the correlation of the data suggest predictable results? Well, going back, this correlation is almost perfect. It would be really interesting to hear what the calculator says it is. Your calculator can display this correlation coefficient, which is called, the calc calls it R, and it describes the reliability of your equation in making predictions. In other words, how tightly clustered are the points to your line. The calculator will also give you the R squared, which gives the percent of error eliminated by using the model. Like I said, if your R squared is 1, you have a perfect model. So to turn that on so that we can see the both R and R squared, we need to go to the catalog, which is the second function of the 0 key. So if you go to second 0, you will have a very, very large menu. And we want to get down to diagnostics on, which starts with a D. So if you want to skip in that long list to the D's, you can hit alpha D, which is the green key, and the key that looks like an x to the -1 because it has a green D above it. So if you hit alpha D twice, I don't know why you have to hit it twice, you do. It jumps to the D's in this list. Scroll down to diagnostics on, and you need to hit enter twice. You hit enter and it asks you if you want it, and you hit enter again. So after you hit enter twice, the diagnostics are on. Then the R and the R squared will appear on the LinReg screen. So now go back to Stat, over to Calc, down to LinReg, hit enter 1, 2, 3, 4, 5, or 6 times, and now underneath are y equals ax plus b, a is 2.5, b is 25. It should say r squared equals 1, r equals 1. So this confirms without a shadow of a doubt we have a perfect fit regression line. The r squared is 1. So the answer to number 10, does the correlation of the data suggest predictable results? Most definitely yes. All right, so I hope that helped with your assignment. Now, I believe you have all the knowledge you need to do section 6.6. So have fun with math.